slightly different answer your question to the interpolation. The problem is we can find the value of n. We can select, for instance, n equals to 3 and n equals to 4, and compare whether they are the same, very similar. If they are the same, then we can select one of them. If they are not the same, we have to increase the degree and then compare again. If they are the two curves are very close, then we say that the fitting is acceptable. And this is a counterexample. I used it to show the Lagrange interpolation algorithm earlier. So for the same problem, if I try to perform interpolation for different degrees, then you can see that the results are completely different. So for this kind of problem, we cannot use polynomial approximations. If n equals to 3, we get a curve like this. The blue one is the theoretical one. N equals to 3, we get a curve like this. If we increase the degree n, we will get this kind of peculiar things. So in this case, we have to say that interpolation may not work for this. The polynomial fitting may not work for this kind of problems. So this is one way to find f of x by polynomials. And the other topic is, once we have a function like this, how can we approximate by another kind of function? For instance, the rational functions where n and d are polynomials. How can we find rational approximations to them? There are several ways to solve this kind of problem. One is by continued fraction. The other one maybe you can use Pelly approximation. I'll talk about that later. Normally, a function can be expressed or approximated by a continued fraction like this. And there are several special forms of continued fractions. And I think the our second form, which always appears in control literature and other literatures, is maybe very useful in actual fitting. And our second form is something like this. And from this, we can see that this expression can finally be expressed by rational forms like this. If we can omit some of the terms, if some certain conditions satisfied, we can omit these terms. And finally, if we simplify the result, we normally can get rational functions like this. So Cauchy form is most usually formed in continued fractions. And Matlab do not have a command to solve continued fraction problems. However, you can code Maple from Matlab. You do not have to install Maple. You can call function like this, and then you can solve continued fraction problems within Matlab. However, this one works only to the version 2008A. It does not work for B or new versions because they have replaced the original symbolic computation engine from Maple to the one called NewPen. Since they have done this one, the command like Maple are not supported. So if you are using early versions of Matlab, it should be okay. So to find a continuous fraction approximation to the original function or original constant, we can use this command first to invoke the number theory package in Maple, and then we can find the continuous fraction by calling cfrac, which stands for continuous fraction. Here are examples. First is, how can we find an approximation to the irrational number pi? To find the fraction, we can give a certain Matlab command like this. First, by calling the package, numerical theory package, and then we can perform continued fractional expansion to constant pi. And in version 2008A, you have to use capital pi. However, for early versions, you have to use small pi. Oh, sorry, this should be a capital pi here. Just indicate. So there are always inconsistency in the versions. So if we use this command, we can find a continuous fraction like this. Of course, you can specify all the terms. There shouldn't be any problems. If you are trying to show that in a theoretical way, what you get is the continuous fraction form like this. And you may see that some of the terms may appear to be larger than earlier terms. You can add a constant there. For instance, this one is much larger than this one. And maybe you have even larger terms. And you can truncate some of the terms and leave only these terms. And finally, you can get a rational approximation to the value of pi. If you only reserve 4 stages of continuous fraction, you can use a command like this. But for numerators, you can use 4 terms. For denominator, you can also use 4 terms and leave the others and omit the others. And finally, you can get an approximation of the irrational number pi by n and d. This is the numerator and the other one is denominator. And finally, you should get a result like this. And you can compare this one with a more exact value of pi like this. You can compare. You can see that with only 4 stages of continuous fraction, you can get a very accurate value of pi. However, if you need more accurate results, you have to increase the number of stages. Up to now, I think it should be okay up to this term. In this case, you only use the 4 stages of continuous fraction. And this is the continuous fraction approximation to a given constant. So if we are trying to find the continuous fraction